Okay. So, we will look into optimization application to energy efficient building design. GA stands for genetic algorithm, it stands for genetic algorithm, right. So, as I said, in building design the decision variables are, I think I was mentioning this, wall material, roof material, type of glass, shape, orientation. This is the decision variables. That means you got to know what should be the best orientation. This is what I was discussing in the last class, and then the combination of the materials in the construction of roof, in the wall, and type of glass, etc. Shading, daylighting, size and placing of window. These are all variables. Ceiling height, type of occupancy, surrounding environment, etc. And obviously, location, budget, color, texture of the exposed surfaces, these are other decision variables. So, so therefore, important parameters of course for building designs are, out of all this, wall material, roof material, types of glass, shapes and orientation. For example, if you look at the previous one back, the location, budget, this we can exclude out for the time being, because that would make life more complicated, but these are part of the wall system itself. Color of the wall, color of the wall, texture, if there is any, one can take. But this example that I am talking of, it takes these 5 variables, right. So, it involves selecting the right combination of design parameters with minimum energy consumption, that is what it is, or maximum thermal comfort. You can increase the thermal comfort or minimize the energy, right. Now, there is something called in design process, something we call backward analysis and something we call forward analysis. Now, what is backward analysis? Backward analysis is the analysis to determine the properties of the inputs of a program from properties of context of the output. What I mean to say is, you have already made a design, then you analyze to find out how the decision variables are performing. For example, if you have already chosen an orientation, shape, etc., etc. Now, analyze this, how good it is, right. And then you change this, change the orientation, analyze it back. So, you get series of answers that way by backward analysis, but a forward analysis would be that you do not start with the plan, you get the plan which will be best for various possible orientation. So, backward analysis, so given the various building parameters, compute the resulting energy implication and improve upon them. So, first you have to have all building parameters are to be known, and then compute the resulting energy implication and then improve upon, right, improve upon. So, you have to assume first, assume the plan itself, design itself. This is what we do in other designs also, some cases. So, such method restricts the design scope as well as the quality of results, because implies that building is already designed. I have already designed the building, chosen the orientation, shape and then analyzed to find out how much. And if I am not satisfied with the design, I change this, I change the orientation, change the shape and come back to it. So, that is process of backward analysis. Forward analysis, which determines the properties of the output of a program from properties of the input, in the sense that determines the levels of decision variables, chooses the orientation from minimum energy consumption. Now, that is why you need an optimization process, because it would first you have to optimize the energy consumption and correspondingly which is the best, which set of orientation, shape they are best, that you can choose. So, this is done by testing of. So, what you can do is you have to have kind of an objective defined, which will minimize the, let us say, energy load or maximize the comfort, and for that from your chosen orientation, shape, etc., which is the best, it will select. So, that forward analysis implies always optimization process. Backward analysis, very long, it is a very long time, does not get best solution, tedious process, and not necessarily it will not give best solution, cannot give global optimal solution obviously. Till date, most work of building thermal analysis has been based on backward analysis. There are several tools or several guidelines available from long time, what you call prescriptive guidelines, right. So, if you are, there is something called Mahoney's chart, it was something of this kind. So, you have tables, if this is your climatic condition, use this, that sort of thing. So, these are all part of backward analysis. Forward analysis, it will give you the best solution and optimal solution, therefore, it has to be done only through optimization process. That is what the importance of optimization process. Now, thermal design process, large number of choices of design parameters, that is what we have seen, there is large number of them, that is what we have seen when we looked at them. Supposing you consider wall, so wall may have 3 layer, just say for the sake of it, simple case, 3 layer. So, one insulation layer, one insulation layer, one insulation layer in between, and then again you have the same layer outside, same layer outside. So, 3 layers. Now, there can be possibility of varying all the layers, right. So, and may have 4 layer wall or 5 layer n layer walls. So, in that case the number of possibilities are very large. Similarly, roof material type of glasses, that is what we have looked into last class, sometime we are looking at 8 into some 4 or 5. So, possibilities are many, basically. So, large number of choice of design parameters are available. For greater degree of energy performance, it is required to optimize the best or nearly best option with this. Therefore, there is a need to find out optimal solution, that we have understood now. The building design optimization process, various parameters involved, some are qualitative and some are discrete. This is what I think I mentioned earlier also, that some of them are qualitative, right, and they are all discrete. Qualitative means northeast orientation, right, north orientation, the long axis facing north, long axis facing northeast, long axis facing northwest. So, these are all qualitative, you cannot quantify them easily, although some angles people have tried with some angles, but many of them are qualitative. Shape is qualitative, that is what we have looked in the last class, and they are discrete, because you do not have continuity from T shape to, let us say, various aspect ratios of L shape, I mean rectangular shapes. Some cases there can be continuity, but most of the cases there may not be. So, this should incorporate such a procedure, design procedure should incorporate qualitative and discrete variable. So, evolutionary algorithm of the kind of this can work on this situation, because it works on coding of the parameter, it does not deal with parameter themselves. For example, you would have done some optimization yourself in some other classes, where you would have had objective function maximize z equals to, I am sure some, even if you have not done, does not matter, it could be, if it is a linear problem, could be C1 or C1 x1 plus C2 x2 etc., or in other words I can write it as sigma Ci xi, right, where these are the, or minimize if it is cost coefficient, this could be profit coefficient, maximize profit or maximize return or something of that kind, and these are linear. So, this is we call as objective function, maximize this. Then you might have had certain constraints which will say that, okay, if it is, you cannot have some values of x and y, x1, x2 might be restricted. So, various kind of constraints there, production constraints that you might have done, but I am not interested here in all those. So, therefore, there is something called objective function which you maximize or minimize. So, in our case maybe minimize the energy load, right. So, that's what you do in this, that's what you do in an optimization process. So, but here my x1, x2 etc. are discrete and maybe qualitative. So, I can codify this x1, x2 etc. If I use them as codes, then orientation number 1, orientation number 2, orientation number 3 etc., I can codify, and my algorithm should work on codified variable. Let us see how we do it. So, GA based is a good one. There are other evolutionary algorithms and modern various kind of algorithms should be available possibly in future also, which will work on codified variables. So, therefore, our objective is to minimize the heating or cooling load of air conditioned building, or maximize the two objectives we can look into, maximize the thermal comfort in naturally conditioned building. Then this all the design parameters must be taken together, all decision variables should be taken together simultaneously and must be able to evaluate the objective. So, my objective function here would be some sort of maximization of let me, if I put it as Z as or thermal comfort. So, I should be able to define thermal comfort in some manner, or minimization of cooling load, or cooling and heating load, some combination which I have shown you earlier. So, if I have to do this, I should be able to either explicitly express thermal comfort in some function form, there should be some way, or cooling load I should be able to express explicitly. Here we can't express them explicitly. That means that I do not have a function which will define orientation x, shape y, what is the cooling load. I can't find that. I can find it through a procedure of calculation. Right, but otherwise I can't find it. So, all the procedure of calculation we may not discuss here, but there are various processes like let us say Estre method, Estre-Beans method, or the admittance procedure, and several other procedures are there through which one can calculate. But I will briefly discuss or give a case study of the situation of optimization here. So, gradually it should improve, it is an iterative process therefore. So, this optimization procedure make a system design or effective functions, these are all right, it is all right, usually contains some elements, decision variable, objective functions I have already mentioned, variables are directly under control and they are the decision variable. So, these are objective function in our case is not a mathematical expression as such, but in our case it is a kind of a procedure through which you can calculate out the cooling load. Some limitations or constraints you may have. Now, what are the constraints in our case could be bylaws, building bylaws could be our constraints, right. So, floor area ratio restriction might be there, and these can form kind of constraints which you should be able to build in. So, there are various kind of optimization tools one can use, as I said, classical methods, gradient methods. So, this is what suits good, is one of those evolutionary algorithms. So, let us see. Okay, this is some history of this, but I do not think I am really, this based on survival of fittest principle, such as vast potential solution space and then comes to the optimal or near optimal solution gradually. Okay. So, fittest solutions are they are allowed to survive, unfit ones are removed out of this. So, simple example will show you. So, first thing is done is coding. So, coded variables are coded. Then how it is done? Variables are coded. Let us say I have 8 orientation, right. I had 8 orientation, let us say. I had 8 orientation, let us say 8 orientation. Okay, no, I am trying to find out a blank space. Okay, let us see something like this. Okay, somewhere I should be able to utilize the space. Yeah. So, 8 orientation, let us say. So, I call orientation 0, 1, 2, 3 orientation, let us say, to 8. One of the simplest way of doing the coding is in binary. So, this I can code it as, since there are 8 such, 7, sorry, up to 7. So, 8 such one in binary, 2 digits 0 0, then 0 1, 2 numbers I can represent by 2 digits. If I represent it by 3 numbers 0 0, 0 0 1, 0 1 0, 1 0 0, right, 1 0 1, 1 1 0 and 1 1 1. So, you can see 1 2 3 4 1 0, I have missed something maybe 1 0 1 I have I have done, and then 1 1 0, then there must be one more. 0 yeah 0 0 0 0 0 1 1 right. 0 1 1, yeah, this is what I was mentioning. So you will have, if it is 3 digits, binary digits, you can use code 8 variables. If it is 4, then 16 possible, 16 cases, you know. So if I have taken 16 orientation instead, then I could have coded them in 4-digit binary, 4-digit binary, right, 4-digit binary, okay. So this is what is done, this is what is done. So first thing is coding, first one is coding. So I code, and that's why I took 8 orientation, 8 shapes, etc., deliberately, so that I can code each one of them through 3 digits. So decision variables, their levels are actually coded in binary form, right, the coded in binary form, okay. So that is the first thing. Then I have something called fitness function, which is a objective function, Then there are operations. What I do? I take a random population to start with, right, random population to start with. That means, okay, now how do I combine this variable? Now supposing I have got orientation, let us say I have just taken state way now, say orientation is 0 1 1, roof orientation is coded, because I will have, let us say 8, each one are taking, I am taking 8 cases of orientation, 8 roof orientation, roof option, 8 wall options, 8 glass option, 8 shape options, right. So let us say this is my north corresponds to 0 1 1, it is coded as 0 1 1. So each orientation is coded as a binary number, 3-digit binary number, right. Line plus RCC, this is coded as 0 0 1. So each wall, you know, roof option is coded as this, in this manner. Now all these are written in a sequence, in the sense that, so this particular case I will write it as 0 1 1, 0 0 1, 1 0 1, 0 1 0, and this was 16 actually, let us say. So this will be one individual choice. I can put them in one single sequence, to combine all the variable together. This gives me one single case. So what I got to do is, I will assume, you know, a population, that means several such cases, which I will generate random manner. So I have to have, in this particular case as I have seen, in this particular case as I have seen, in this particular case as I have seen, I will have 3, 3, 6, 3, 9, 3, 1, 2, 3, 4, 4 into 3 is 12 plus 4, 16. So I have a 16-digit binary number, which represents a case. Now how many total cases will be there in this case? 8 into 8 into 8 into 8 into 16. So that many number of cases are possible, out of which I select randomly some number which is based also on principles, and then do the GA operation on them. So that is what I do. So GA begins with a population of random strings, representing combination of decision variables. So a string represents combination of decision variables, right. Thereafter fitness value of each string is evaluated. Now with this case I can evaluate the fitness value through any one of my procedure. For example, if I have a procedure for calculating the cooling load, then for this case, this particular case, I can calculate out the cooling load. I am not explaining how to calculate out the cooling load, but as I said, there are there are ways, solution procedures through which you can actually determine the cooling load for the given string. So fitness value of each string is evaluated. 40 of them, if I have taken to start with 40, a population of 40, then I have evaluated all of them. Then you operate GA operator and create a new population. That means what I do? I remove those which are not fit and keep only those are fit. Now, that would obviously reduce down. If I started with 40, it will reduce down to something like some number, let us say 20, 18 or 15 or whatever it is, depending upon how we have selected the initial 15 or 16. Now, this 16 has to be again made into 40. This is by what is called a crossover. New population is generated out of this. I will just explain this again. So, new population or new strings are created out of this 16, again I bring back 40, I make 40 new string, new one, and this 40 again I evaluate, and this process continues till I get the no improvement in my results. So, let us see how it is. New population is treated again till optimized, and one cycle of operation is called a GA operation in GA terminology, and once you find out the best, then you can decode it to find out what was your solution, because the coding sequence so you can come back, right. So, this is how it is. For example, say coding, if orientation is 0 1 1, this is then decode, because I already know what these are, right, simple glass and so on. So, shape option was L 24 or 12, etc., etc. So, first is encoding, all options, orientation, roof wall, those are done, encoding. So, you make them into sort of string, right, and then decoding is the last one. So, how do we go about it? Let us say this is roof option 1 is this, roof option 2 is this is north south. I have defining it, coding them, already done the coding that way. Wall option 1, wall option 1, that could be wall option 2 or something like this, glass option 1, glass option 2 and so on. So, shape option and so on. So, what it does, if I have this, then the population would be 0 0 0 1, the blue represents roof option, wall option 1 0 1 and glass option 1 1 0 and shape option 0 0 1 1. So, this is the first one, this is the second one, the individual from in the individual 2 in that population, if you have 40 or such things. So, 2 of them, right, 2 of them. So, there would be pair, we work in pairs. So, there would be 20 pairs, let us say, to start with, right, and what we do is we select the best and keep this out. Now, how do I do that? We use, supposing I have evaluated all 40 of them. One of the simplest ways to do by what is called a roulette wheel selection, random selection. So, what you do is, you see, you find out the fitness values, and fitness values which are only 4% fit, some might be 7% fit, some must be 32% fit. Okay, this will become clear through an example. I will come back first to. So, this is the simplest way of selection actually. For example, if this is the example, if I take, this is my fitness function, f x is equals to minus 4 x squared 2 x plus 5, and I use, these are called chromosomes, each string, and its decimal value I am representing it by 6 plus 10 digit number. Say, so decimal value of this one would be, how much is the decimal value? Because we know 0, 0, 1 is 2. So, decimal value, how it is calculated? Binary decimal values 0, 0, 0, 1, then 1, 1, then 0, 0, 0, 0, 0, 1, 0, 1, 0, then 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1 first, then 1, 1, 0 and 1, 1, 1. So, you can see that this number is how much? This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, 8, So, you can basically, how do you represent? If it is number of digit, sorry, this is if it is 2 digits only, if it is 2 digits only, it will be 2 to the power 1 plus 2 to the power 0. If it is 3 digits, 2 to the power 2 plus 2 to the power 1, how many of them will be there? 1, 2, 3, 4, 5, 6, 7, 8, 2 to the power, no, this one is 0, 0, 0, 0 is not there, 2 digits, sorry, it will be 2 to the power 3. So, 2 to the power 3. So, supposing I am denoting by 2 to the power, this would be how much? This would be how much? In binary, this I want to convert this one into regular number, that is our decimal value, It will be a 3 digit decimal value, a 3 digit decimal value, supposing I have 1000. This, if I have 2 to the power 4, that is 16, 2 to the power 5, 2 to the power 5, 32, 2 to the power 6, 2 to the power 6, 64, and 2 to the power 7, 128, 2 to the power 8, 256, and 2 to the power 9, 256 into 2, 512, and 2 to the power 10. That is why the 1000, the 3 digit values I will represent by 10 digits. So, this is just as an example. Now, if you take this value, how much this value would be? Because this would be 2 to the power 0 into 1 plus 2 to the power 1 into 1 plus, so if you add this up, you actually convert this binary into digital, you will get 107. Similarly, if you convert this, you will get 985, 260, and so on and so forth. Now, anyway, we can look into this again if required. Now, x is equals to, we are taking x value, defining x, this is my objective function or fitness function, x is defined in 0.977 decibel value divided by 100. Just arbitrarily, this I am saying, this is a function of x which is defined like this, the decimal value divided by 100. So, this is my x value, the fitness value calculated according to this function is 6.82, and in this manner I can calculate the fitness value for each of these cases, because this will be 107 multiplied by 0.977 divided by 100, 105, 985 multiplied by 0.977 divided by 100 is 962, and so on. So, if I sum them up, this is 22.06. This is 31% of, this would be, okay, if this total I call it 100, and this is, if you see this, if I divide this 682 by 22.6, I get 31, 1.1 divided by 26, I get 5, and so on and so forth, right. So, I can arrange them in ascending order, arrange them in ascending order, 1.1 5%, 2.57, then 12%, and next one is 3.14, then 6.8 to 31, and this is 14%. So, I can find out probability of finding, so this is basically nothing but relative frequency in percentage, this is relative frequency in percentage, 31% of the, this is 31% fit, 31, in the fitness scale, if you look at it, 31% is this. So, how do we find out probability? Probability is basically 31, is 0.31, probability of finding, probability of this is 0.31, probability of this one is 0.05, and so on and so forth. So, these probabilities I can find out, and I can generate now random numbers. So, for example, I generate random numbers. If I generate random numbers, if it is between 0 to 5, right, the lowest one is 0 to 5, then I repeat this. If it is between 5 to 17, cumulative 5 to 17, then I will choose random 2 digit random number I can generate. So, if the number is between 00 to 05, I will repeat this. If it is 5 to 17, that means 0, 6 to 17, 5, 12, 5 plus 12 is 17, I will repeat this number, right, because I got to generate more population. And if it is next one is 17 plus 14, so between this then I will generate this number, and if it is beyond that then I will generate up to 31, and last one would be 38. So, I would actually generate, this is the largest value of the fitness, and this has got a chance of being selected 38%. The one which has got the largest value of fitness, because I am summing them up and dividing by the cumulative value, total value. So, this will be repeating itself 38% of the time, this will be repeating itself 31% of the time, and the one which is small, the fitness value is small. So, what I am doing, I am summing up all the fitness value. The largest fitness value, this will have this percentage highest. Supposing the sum total was 22.6, and let us say this was something was 10.1 or something, right, out of this. So, 10.1 divided by 22, that would mean that 50%, more than 50% chance I will select that. So, whichever has got the highest value here, it has got the maximum chance of being selected. So, because I am generating random number, now I will select them accordingly. So, this will have 38% chance of being selected. So, probability of selection is defined by this f x I values divided by sigma f x I. This will have 31% probability of selection, this will have 14% probability of selection, this will only 5% of selection, which means that when I complete the population back again, I will have majority of this number, which gives me highest fitness for this function. So, same thing we can repeat for our building case also. So, the fitness value which has 32% chance of being selected, that I can write in a pie diagram like this, 32%, something 13%, etc., and generate random number between 0 to 100, right, or depending upon how many variables you have taken. 0 to 100 is good enough. So, because it is 2%, only 32%, I am talking in percentages. So, the fitness value corresponding to this will have the highest chance of being selected, right, and the one, this will have less chance of being selected. So, once you have selected, created a new population now of the same number that you have started with, then we will do something more. So, we will just wait for a minute and answer some of your questions and then come back to it again.